All right, so good evening, everyone. I'm going to talk today about the principle of mathematical induction. So the principle of mathematical induction is basically a way by which we do a lot of mathematical proofs. So we start from a basic argument, and then we try to find a general argument or general solution from that argument. So if someone says this person is a liar, we want to say, we want to check, has this person told a lie before? Um, did he tell a lie again? And can we use that as a basis of argument to say that this person is a liar? So this is really a logical conceptual proof that is used in mathematics a lot as well. So what is the definition? It is a technique of proving a statement, right? Proving a statement, theorem or formula which is thought to be true for each general proposition, right? Propositions which are said that something is true for all for all positive integers or for all positive integers from some points. Right, so this is the part that is really interesting, that it may be true from some point. So one has to consider that as well. Okay, so um, the technique usually involves two main steps. The two main steps being that if we want to follow this technique, there are two main steps we need to consider. So the step one is that we have a base step. We need to prove a statement is true for the initial value. And then for step two, we prove for the inductive step, which says that here, if we know that the k step is true, then the k plus 1 step will also be true. So we put this in perspective in a theorem, a statement of facts, that says that if we take Pn to be a positive statement about a positive integer n, and we suppose, so here Pn, if you see it as that, then we suppose that P1 is true, then we can say that Pk plus 1 is also true whenever Pk is true. So this is a statement of fact, that a statement that if you take a Pn, then you say that if Pn is true, then you can test for P1, and then you can assume that if Pk is true, then Pk plus 1 will also be true. So let's take a few examples to illustrate this whole idea of the principle of mathematical induction. So example one, if we take the sum of all positive integers, or let's say the sum of natural numbers, which is 1, 2, 3, 4, 5, 6, 7, up to a certain number n, we say that that sum, we can easily get it as also n times n plus 1 into bracket over 2. Right? So, of course, it shouldn't be that complicated to see it, because if you take 1 plus 2 plus 3, that is the third term, and you add them, you will get a 6. And the same thing if you take this formula here on the right. So let's call this thing here the right-hand side. And let's call this part here the left-hand side. Okay, so what does the principle state? The principle of mathematical induction says if you are given a question that prove by mathematical induction that the left-hand side of a statement is equal to the right-hand side of the statement, then you start by saying, okay, if Pn, so this is our Pn is a statement 1 plus 2 plus 3, and so on is equal to n, and this is the same as n plus 1 over 2, right? And then we have that if you take n is equal to 1, right? If you take n is equal to 1, then on the left-hand side, so you have to consider the left-hand side of the statement of Pn. On the left-hand side, we'll have that P1 is equal to 1, right? This is the first value on the left-hand side. And this means that P1 is equal to 1. If we take the right-hand side means that we now take n is equal to 1 because that is what we are considering for n is equal to 1. So for n is equal to 1 on the right-hand side, you substitute 1 into n. And here you have 1 into bracket 1 plus 1 over 2, and this is equal to 1. Okay? So here we say that P1 is true since the left-hand side of P1 is equal to the right-hand side of P1. So if you take the left-hand side, you have P1 is 1. If you take the right-hand side, you have P1 is also 1. Now, if we assume that Pk is true, which is the inductive step, you assume that Pk is true, then by induction hypothesis, you say that 1, your Pn, now you rewrite your Pn as Pk. So we write that Pk is true. So if Pk is true, then we have 1 plus 2 plus 3. You should look down here, plus 4 plus and so on, plus k is equal to k into bracket k plus 1 all over 2. So this is our Pk. So we assume that our Pk is true. If Pk is true, then we say that Pk plus 1 will just be that now we can write Pk. So we can write this term here now and include a k plus 1 term. And the same we can do for the right-hand side, a k plus 1 term. So if we do that, then you see that we add here on the left-hand side a k plus 1 term, and then on the right-hand side here, we also add a k plus 1 term. So if you do this, then you can see you can just factorize k plus 1 out, right? Because there's k plus 1 over 2 plus k plus 1. So you can factorize k plus 1 out, and then if you do that, you'll be left with k over 2 plus 1 in brackets. And if you have k over 2 plus 1 in brackets, you can write that as k plus 2 over 2. And then you multiply it with your k plus 1. So in essence, you have k plus 1 into brackets, k plus 2 into brackets over 2. And this is exactly corresponding to your pk plus 1 value. So we say that since pk plus 1 is true, then we can say that Pn is also true for all n greater or equal to 1. So let's take another example. In the next example here, what we're going to do now is also to consider a mathematical proof of induction that the cube, right? The sum of the cube of all the natural numbers is going to is equal to n squared n plus 1 squared all over 4, right? So that is if you take the sum of the cube of all the integers, you should get n squared n plus 1 squared over 4. How do you show this again? So we say that Pn, our statement, let P of n, right, be equal to or is given by the left-hand side. So this is the left-hand side, right? And then this is the right-hand side, So our Pn, and this is what we call our Pn statement. So now we take the left-hand side, we take n is equal to 1. So for n is equal to 1, on the left-hand side, we have 1 cube. And 1 cube is equal to 1, right? So here it's equal to 1. And then we take on the right-hand side, if we take n is equal to 1 on the right-hand side, then here you have 1 squared into bracket 1 plus 1 squared all squared, right, over 4. And if you put in that, then you see you also get 1, as rightly down here. And so we say that the left-hand side of P1 is equal to the left-hand side of P1, the right-hand side of P1, so P1 is true. Now, the inductive step. So this here is the inductive step, right? The inductive step. So in your inductive step, you assume PK is true. If you assume PK is true, then you say that you can write that 1 cube plus 2 cube plus 3 cube all plus k cube is equal to k squared into bracket k plus 1 squared all over 4. And this is exactly what we mean by PK, right? The PK. So we assume that this is true. If this is true, then we say that for the k plus 1 value, we can add here a k plus 1 term, right? This is the k plus 1 term. So again, so this here, all this here is our pk. And then this is the k plus 1 value, right? That is now added. So in a similar way, we take all this here, right? We take we go now on the right hand side and we see that this here is the pk value. And now we add again a k plus 1 value. If we do that, then we will see that we can simplify, right? We can now write everything over 4, and that means that we multiply the k plus 1 value by 4. We divide, we simplify again, right? We simplify, and then we finally come to the value of k plus 1 squared into bracket k plus 2 squared all over 4. And this is exactly what we mean by the pk plus 1 value. Of course, it's easy to just check also the pk plus 1 value. Basically, take your pk and then take the right hand side and then substitute the k plus 1. You do that, then you have k plus 1 squared. Then you have k plus 1 squared all over 4. And this will be k plus 1 squared, right? K plus 2 squared all over 4. So it's a bit straightforward in that sense if you want to check it in the end as well, just for verification purposes. All right, let's take a bit more of an exciting example on the third example. So in this third example, I want to prove that by mathematical induction that if you have 23 to the power n minus 1, it is divisible by 11 for all. So we say that 23 to the power n minus 1 is divisible by 11 for all n greater or equal to 1. This is what we are trying to show here in this example, right? So you need to take your Pn value, right? Your Pn here is 23 to the power n minus 1 is divisible by 11. Now, if n is equal to 1, then we have 23 to the power 1 minus 1, which is 22, and 22 is divisible by 11. This is true. Now we go to the inductive step. So this is the inductive step, right? This here is the inductive step. For the inductive step, we assume pk is true. If we assume pk is true, then it follows that 23 to the power k minus 1 is equal to 11 times m. So this value we have here, this here, right? We can say that is equal to an m, right? And this m should be an integer. This m here should be an integer. If it is, then of course we say that 20, then we can say that this value here will be divisible exactly by 11. So we say 23 to the power k minus 1 is equal to 11m, where m is some integer, right? Some integer, positive integer. Then the k plus 1 step. So the k plus 1 step just means now replace the k here by k plus 1. So we say 23 to the power k plus 1 minus 1, and now we expand it, right? So 23 times 23 to the power k minus 1. So we want to find a way to show that this value on the left is truly divisible by 11. So we say that our minus 1 here, we can write it as minus 23 plus 22. And that means that we can now factorize this first part of the equation. We can factorize this first part of the equation and our new value minus 23 that we've added. If we do that, then 23 comes out. Then we have 23 to the power k minus 1 plus 22. Of course, we know what 23 to the power k minus 1 is. 23 to the power k minus 1 is exactly given by what we have said here is equal to m. So we can substitute that 23 to the power k minus 1 is equal to 11m. And if we do that, then we can see we can factorize 11 out. And then if we factorize 11 out, we'll have 23m plus 2. So this is 2. Value here should be 2, right? If we do that, then we can have here the value here should be 2. Okay, so if we do that, then immediately we should be able to have here, right? We should have here all right, we should have here 23m plus 2. Okay, so and that means that now we can write that this value here, right, is also a positive integer. It's in the positive integer because m is in the positive integer, and so this is also true. So this is also true for that. And then finally, something that you need to think about. So for instance, if I give you this question here, which I say that the number of diagonals of a convex polygon with n vertices is n to the bracket n minus 1 over 2 for n is equal to 4. And I say show, right? Show by mathematical induction. Let me write a show by mathematical, right? Mathematical induction, right? Induction that the number of diagonals of a convex polygon, right? Of a convex polygon, oh, of a convex polygon is n minus 3 over 2. Okay, so here, of course, I'm not going to solve this for you because you have to think about it a bit. So, but to give you a hint, what you need to do is you need to ask yourself, what is the Pn statement, right? The Pn statement says n over 2n minus 3 for n greater or equal to 4 is true, right? It's true. So it means if n is 4, this is where you start from. If n is 4, then we have P4 is equal to 4 over 2 into brackets 4 minus 3, which is 4 over 2 into brackets 1, and this is equal to 2. And you can check if you have a convex polygon, so convex polygon of vertices 4. This is 1, 2, 3, 4. Then you know that truly there are 2 diagonals. So if n is 4, then we know that the diagonal is 2. Right? And of course, we can do similarly if n is 5, how many diagonals would we need? So if n is 5, right? If n is 5, then here I draw pictorially. So if n is 5, then you have 1, 2, 3, 4, 5, right? If n is 5. And then in that sense, you can count how many diagonals? 1, 2, right? 1, 2, 3, 4, 5. Right? So if n is 5, P5, Then we have 1 over 2 times 5, 5 minus 3, which is 5 over 2 times 2, which is 5. So you see, if we have 5 vertices, the number of diagonals is 5. So we can continue in that sense, but we need to make an assumption, right? We need to make an assumption, right, for to be able to conclude on a proof on a certain formula, right? So this is for you to think about. So if you have the pk plus 1, you should be able to finally show that, for instance, if you have a pk plus 1, you will get um you will get 1 over 2 k plus 1, and then you get k plus 1 minus 2. Okay, something like that. So this is a do-it-yourself activity to show that this is true. Okay, and then with that, we come to the end of mathematical induction.